Bismillahirrahmanirrahim. Dear students, grade 12 chemistry and the lecture number 68. We are talking about the last chapter, nuclear magnetic resonance spectroscopy. The last topic of this last chapter is spectroscopy, complete topic, and we are doing nuclear magnetic resonance and page number 349. Now instrumentation. Students, there are two types of spectrophotometers which are commonly used for nuclear magnetic resonance study. Number one is called NMR. Number one, continuous wave. Continuous wave NMR spectrophotometer. This is number one. Number two is Fourier. Fourier transform. Fourier transform NMR spectrophotometer. There are two NMR types. In the continuous wave NMR spectrophotometer, number one, the frequency of electromagnetic radiation is kept constant. The frequency of electromagnetic radiation is kept constant and the strength of applied magnetic field is gradually varied to sequentially bring the precessional frequency of all the nuclei in the response with the frequency of the electromagnetic radiations. The spectrum is recorded directly as absorptions versus frequency, and it takes several minutes to complete. This is the continuous wave NMR. In case of FT, NMR spectrophotometer, the strength of applied magnetic field is kept constant. This is the difference between the CW and FT. This is the difference. Here in the FT NMR, the strength of the applied magnetic field is kept constant and the radio frequency is applied at a single short duration in about microseconds. So powerful pulse, a burst of radio frequency energy which effectively covers the whole frequency range to be studied. The signal detected in this case is recorded, digitalized and stored in a computer as an array of numbers. So the Fourier transformation, a mathematical treatment from the CW spectrum. In the CW NMR spectrophotometer, we measure the radiant energy which is absorbed. Whereas an FT nuclear magnetic resonance spectrophotometer. It is the energy emitted by relaxing nuclei which is measured. The CWNMR experiment provides an absorption spectrum, whereas pulsed FT-NMR experiment provides an emission spectrum. So dear students, on the page number 350, there is a 24.7, a simplified NMR spectrophotometer. The sample is dissolved in a solvent such as water or carbon tetrachloride, which does not have a nuclear magnetic properties. So you have a magnetic radio signals generate the magnetic, powerful magnet north and south. There is a test tube which is going to be, a sample is going to be added, radio signals you can see, and there is a recorder and it is going to be passed through detector. Through the peaks you can get the result, computerized results. So students, the techniques of nuclear magnetic resonance is particularly useful for the identify the number and type of hydrogen atoms. Hydrogen 1 atomic number in a molecule. It is also used to find the position of carbon atoms. The common isotope of carbon must be 12 carbon and hydrogen 1. By using NMR, so carbon 12 does not have a nuclear magnetic, but natural carbon contains 1% carbon 13 isotope, which does show magnetic behavior and can be identified using nuclear magnetic resonance. Even number carbon 12 does not have a nuclear magnetic, but natural this carbon contains 1% about isotope of carbon 13, which can show the magnetic behavior and can be identified by using this instrument. So dear students, there is an example is ethyl benzene. Ethyl benzene C6H5 CH2 CH3, or this is the ethyl benzene. Ethyl benzene. So dear student, you can see this spectrum, and on the x-axis you see the chemical shift, and the y-axis there is a intensity of absorption. This NMR spectrum of ethyl benzene, this is the portion of NMR spectrum, the frequencies of corresponding to the absorption of energy by hydrogen 1 mass nuclei, which are proton. Notice that there are 3 major peaks. 3 major peaks. You can see 3. C6H5, CH3, CH2. C6H5, CH3 and CH2. So dear students, in the spectrogram you have a spectrum here. the longest one single peak A, which shows 5 units of hydrogen, means C6H5 on the left side, long peak, single long peak. So each peak corresponding to the hydrogen atoms in a different molecular environment. This area under each peak is proportional to the number of that type of hydrogen atom in the molecule. So I told you the longest peak A which shows C6H5, 5 hydrogen atoms. C6H5 means arene, benzene ring. It shows benzene ring, arene. Second longest peak on the right side, 3 units, you can see 3. Peak C is about CH3, 3 hydrogen atoms, CH3. Second largest C peak corresponding to the 3 hydrogen atoms in this methyl group, and middle 2, you are seeing the 2 peaks, smaller 2 peaks, and here are 3 peaks, and here is the one's longest peak, B peak 2 units, methylene group, CH2, methylene. So we use as a reference TMS, tetramethylsilene, TMS. Tetramethylsilene. Tetramethylsilene, TMS. I will explain this. So the hydrogen atom in a particular type of environment have the similar position in NMR. If there are many CH2 group, they will give same position. CH3 different position, CH2 different position, arene different position. So in the NMR spectrum, normally this position is measured as a chemical shift. Chemical shift from the fixed reference, you can see here from 0, it starts from 0, and there is a reference point normally used in the absorption of substance, which is known as a TMS standard, which has no absorption, 0 absorptions, and its chemical shift is 0, which is a tetramethylsilene. A hydrogen atom in a particular type of environment have similar position in the NMR spectrum. Normally this position is measured as a chemical shift. This is a chemical shift starting from 0 to 10. And also a reference point normally used is absorption of substance known as TMS, which has a non-toxic unreactive substance, which is chosen as a reference, 0 chemical shift. So the chemical shift TMS is set as 0. TMS is a tetramethylsilene, non-toxic and unreactive substance, is chosen as an NMR reference because its protons give a single peak at 0, and it is well separated from the peaks found in spectra for the most organic compounds. So you can see the table 24.8, the chemical shift is going to be 0 to 10, and it's going to be increased, and TMS, which is a standard, which is a adjusted at zero, and organic compounds can be analyzed according to their types of hydrogen. So dear students, this is the nuclear magnetic resonance, and according to instrumentation. Whole topic is included: spectrophotometer, spectroscopy, whole topic is included, complete topic is included. You have to study the complete topic of spectroscopy, and you have to solve the quick quizzes written here, and you can see from the textbook, as well as exercises questions. Now we start another one, which is called atomic emission spectroscopy. Atomic emission spectroscopy. So in the atomic emission spectroscopy, it pertains to electronic transitions in atom, electron transition, which use an excitation, means electron jumps from lower to higher. This is called excitation. So we use a flame source, spark. Flames spark we use for excitation purpose. Emission spectroscopy is related to atoms. Emission spectroscopy is concerned with the characteristic radiation produced when atoms are excited. They emit radiations in the form of discrete wavelength of light. Wavelength of light, we call them spectral lines. By returning to the lower energy states to make stabilize, when it is going to be excited, energy is absorbed, radiations are absorbed. When there is a de-excitation, then amount of the radiation is going to be evolved. So this is the introduction about the atomic emission spectroscopy. Now what is the principle for this? The source, I told you, we use a flame spark. Source vaporizes the sample. We put the sample to be analyzed, is changed into vapors, and the sample and causes electronic excitation. Already I told you of elementary particles into gaseous state, vaporization taking place. Then excited molecules in the gas phase emit band spectra. Band spectra. Thus, the molecule in an excited state, energy E2, undergoes a transition to a state of lower energy E1, and a photon of energy Hv is emitted. You done the Planck's quantum theory. Planck's quantum theory of radiation, that E is equal to delta E. Change in energy is equal to E2 minus E1. That is equal to H frequency, or E is directly proportional to the frequency. H is a Planck's constant, and there is a frequency difference of energies. Each electronic state, a molecule may exist in number of vibrational and the rotational states of different energies. Now, types of spectrum. Spectrum may be classified as, I told you earlier, continuous, emission spectrum. Continuous emission spectrum and line or atomic emission spectrum. Line or atomic emission spectrum. So, in the continuous spectrum, when you pass white light through prism, it disperses into 7 colors. This dispersion of light into 7 colors is called spectrum. All the colors are in the visible region from 350 or 400 to 750 nanometers. They have a fixed position starting from the violet and end to red, and this is called waveguide. All the colors are merged with each other. You can't mark the boundaries of these colors. It's called continuous emission. Energy is emitted. In this case, you can see the diagram. So when the light is passed through the prism, it spread out into band of 7 colors on the screen. The 7 colors diffused into each other. The boundary line between the colors cannot be marked. That's why it's called continuous emission spectrum. Atomic or line spectrum. Students, this line spectrum is a discontinuous, and there are 2 types. Absorption line spectrum and emission line spectrum. Bohr model. Dear students, if electron is here and suppose it is excited by giving energy, this is the excitation from E1 to E2. So electron jumps from E1 to E2 excitation, it absorbs. And the spectrum is only formed when it revolves in a particular orbit. The spectrum is only formed when the electron is revolving in a particular orbit. So when it passes through this space, the color is vanished, spectrum is vanished, shows discontinuity. So in this case, when electron is excited from E1 to E2, the line spectrum is called absorption line spectrum. Absorption line spectrum, and you will find the large white boxes are separated from very small black lines. Large white spaces are separated by very dark lines, is called absorption line spectrum. Students, when the electron is de-excited, from E2 to E1, there is a de-excitation now. So the amount of energy will be emitted. In this case, this spectrum is a line emission spectrum. And in this form, you will get a black large spaces are separated by white lines. White lines you can see. White lines are separated by the black big spaces. It shows that energy is emitted, light is emitted, and dear students, because electron travels some distance, if jump from lower to higher or fall from higher to lower, same space is going to be covered or distance. That's why lines between the emission spectrum, the position of the lines in the emission spectrum and absorption spectrums are 100% same, equal. So when an element is vaporized in the flame, I told you, or an electric spark in the discharge tube, it emits light in the correct color. The resolution of the ray of this light produces colored lines separated by the dark spaces. I told you this is the emission spectrum. This type of separation is called emission spectrum. So each element has its own correct color, and we can identify by the flame test. Sodium gives the yellow color on the Bunsen flame. The strontium gives the red color on the Bunsen flame. Potassium gives the violet color on the Bunsen flame. In the similarly discharge tube, neon glows with the orange red color, helium glows with the orange pink color, hydrogen glows with the orange red and blue color, and chlorine glows with the orange green color. These are the spectrums, and the lines in the spectrum of an element are not haphazardly distributed, but they occur in the group or series. In series, the separation between them decreases regularly as their wavelength decreases. At a certain limiting values, the spectrum becomes continuous. You can see in the diagram. Slowly and gradually decrease wavelength and become now continuous after the time passes. So this is these are the types of the spectrums: continuous spectrum and line spectrum. And I told you there are two types of the line spectrums: emission line spectrum and absorption line spectrum. Advantages. Advantages of line emission spectrum. This technique is highly specific. This method is extremely sensitive. With this technique, all the metallic elements can be detected, even if they are present in the very low concentrations. Even metallites can be identified by this technique. This analysis can be performed either in the solid or liquid state with almost equal convenience. This technique requires minimum sample preparation, as a sample can be directly introduced into the spark, solid or liquid. The technique provides result very rapidly. If automated, time required is just 30 seconds to 1 minute. This method has been used for wide variety of samples like metals, alloys, paints, geological specimens, environmental and biological samples can be analyzed by using this technique. So students, there are advantages, but there must be also disadvantages. Disadvantages. The equipment is costly and wide experience is required for successful handling and interpretation of spectra. It means that the chemist, the worker, the engineer which works with this instrument must be most experienced person, and also it costly. Recording is done on the photographic plate, which takes some time to develop, print and interpret the results. Radiation intensity are not always be reproducible. Relative error exceeds 1 to 2%. The accuracy and precision are not high. So these are the disadvantages in the emission spectroscopy. Applications, I told you, emission spectroscopy has been employed to determine the impurities in nickel, manganese, chromium, silicon, aluminum, magnesium, or silice, tin, cobalt, vanadium, lead, bismuth, phosphorus, molybdenum, iron, even steel in metallurgical processes. You can use alloy also, zinc, copper, lead, aluminum, magnesium, tin can be analyzed. Lubricating oils have been analyzed because they contain metals like nickel, iron, chromium, manganese, etc. Concentration of metal in the liquid lubricating oils has increased during the course. It indicates excessive wear and tear need for engine overhaul. In petroleum industry, oil is analyzed for the vanadium, nickel, iron, the presence of which make fuel poor. Solid samples and animal tissues have been analyzed to several elements including potassium, sodium, calcium, zinc, nickel, iron and magnesium, etc. Emission spectroscopy has been used to detect 40 elements in plants and soil. Thus, metal deficiency in plants and soil can be diagnosed. So, these materials can be analyzed. Trace and major constituents of ceramics, traces of cobalt, nickel, molybdenum and the vanadium in graphite, trace metal impurities in analytical reagents, trace of calcium, copper, zinc in blood. Zinc is pancreatic tissue, so can be detected here. So dear students, we are going to be close here, and in the next topic we will study other spectroscopic technique, atomic absorption spectroscopy in the next lecture. Then we will have another one, 2 topics more, then we will finish the syllabus and you have to revise more and more. Thank you very much.